Hi, so we're going to talk a little more about what happens in alpha decay and in beta negative decay. We're going to look at exactly what happens to an atom when it undergoes these things and how to write it like in a reaction form, how to show someone what's going on. So we're going to start with the alpha decay. Let's talk about what alpha decay is for a second. Now, if you watch the other videos, if you went through what each of these processes are, you'll see that in alpha decay, we emit an alpha particle. Okay, that alpha particle is composed of 2 protons. Now, throughout the year, I'm going to use symbols to represent protons and neutrons and electrons. We're not going to see the protons and neutrons much longer, but a proton is always going to be a P with a plus, and then it has 2 neutrons also. That's an N with a 0, right? Because there's a positive charge on a proton and a neutral charge on a neutron. Okay, so my alpha particle contains 2 protons and 2 neutrons. Well, because it has 2 protons in it, we know that it really is a helium atom. Anything that has 2 protons is helium. So my helium atom here, 2 protons, 2 neutrons, and I'm going to keep saying it. I'm not sorry. Okay. If I want to write it like the isotopes, like we did on the table, I put the atomic number on the bottom. Well, there's 2 protons. That gives me an atomic number of 2. And then I put the mass number on the top. Well, I have a sum of 4, and that's what my mass number is the sum of my protons and my neutrons. So I'm going to put a 4 up here. That's my alpha particle. So when I want to write out what happens when uranium-238 undergoes alpha decay, we're going to start with the uranium atom. Okay? Write the symbol, and then we need the numbers over here. Once again, the top number is the mass number. Well, how do I know the mass number? Well, it's right here in the name, right? Uranium-238. The mass number is 238. So then what number goes down here? Well, you get out a periodic table, and you look up uranium, and you see what atomic number it has. Once again, the atomic numbers are the in order whole numbers that go 1, 2, 3, 4, 5, 6, 7 all the way through the table. It's usually it's always the largest font number. It's usually at the top. Sometimes both numbers are at the top, and sometimes they arrange it a little bit different. But it's always a whole number, and it's always the number that's in largest font. For uranium, that was 92. Okay, so I start with this uranium atom. Then throughout the year, we are going to use one big arrow to the right to represent, and then something happened. I start with this, and then something happens. Now this something this time is alpha decay. Okay, when we undergo alpha decay, right, just like we were talking about, we lose this helium atom. So after it undergoes alpha decay, it spits out the helium atom, 4 and 2. Okay, but that's not the only thing that comes out of it. It throws away this helium atom. It's got this as an extra piece, but there's got to be some stuff left over. Okay, let's look at what that is. Well, I started with the mass number for my uranium of 238, okay, and then I lost 4. So if I start with 238 and I lose 4, I should have, when we're done, 234 mass left over. And the same thing with the 92. I start with the 92 and I lose 2 protons, which means that I'm going to have 90 protons left. Well, is this still an atom of uranium? It is not, because all uranium atoms have 92 protons in them. Well, this doesn't anymore. Now it only has 90 protons in it. Okay, so what is this? Well, you get out a periodic table and you look up what would have 90 protons then, okay, and it will tell you the answer is thorium, which is a TH. Okay, that's a very good H, but okay. The one thing we do need to add still to this is, in addition to alpha decay and beta decay and all of our other decays, what comes along with all of these things is that gamma radiation. Now, the symbol for gamma is kind of like a funky looking loop. It looks like that. Okay. If you're going to type it, you're welcome to just put a Y in there and pretend that it's that funky little loop. Or if you're an overachiever and you want to go into something and find the special characters and figure out how to make that actual gamma, you're welcome to do that, or you can draw that funky little loop. If you're drawing them by hand, any attempt to make that thing makes me happy. Okay, so this is our alpha decay. Now on the worksheet that you're going to be asked to do, the answer is not simply thorium-234. The answer is all of this. Okay? This corner here, there we go. This corner here is notes for us, like an idea of what's going on. This is an example. This is what I want your answers to look like. Okay, so we'll do another one. Well, do a different one now. So what if I have beta decay? We're going to do beta negative. We're not going to worry about beta positive because it's just one more thing. Let's look at beta negative decay. Okay, I have sulfur 35, and it's going to undergo this beta negative. Well, in our alpha particle, I had 2 protons and 2 neutrons. A beta negative particle is actually simpler than that. Beta looks like that, by the way. Okay, beta negative particle is just an electron. Okay. Now I still need numbers on it, right? This is a mass number. This is an atomic number. So how much mass does an electron have? Well, you look things up and remember that an electron actually has 0 mass. There's no mass in an electron. And then this bottom number is an atomic number. It tells me how many protons are in this atom. Well, there are obviously no protons in an electron, right? It's its own thing. But it also has the opposite charge, and because of the way that beta negative ends up working, we're going to put a -1 down here for its atomic number, because this electron has a -1 charge. Okay, so we're going to do the same, start the same way. We look at the element that we've been given, and we write an atomic symbol for it. So we have an S for sulfur, and then the mass is 35. Okay. And then I need the atomic number down here. I look it up and I will see that sulfur is 16. Okay? And then something happens. This time the something is beta negative. Okay? And what comes out of it? Well, this time I'm going to lose the beta particle, right? So every time you're going to start with the original atom that's in the question, and then you're going to put the particle for the thing that's happening. So here I started with my uranium, and then I put my alpha particle because that's what's happening. Now I'm going to start with my sulfur, and I'm going to put in my beta particle here. So E0, -1. Okay. Plus, we look to see what's left over once we lose that particle. So I had a mass of 35, and my electron takes 0 mass with it, which means that my mass is still 35. Okay, ready? And this is the hardest part, trickiest part of the whole problem. I have 16 protons. The atomic number on my electron is -1. So if I had 16 and I lose -1, it means that I'm actually going to end up with 17. Now, the reason that we actually end up with 17 has less to do with the electron and more to do with the fact that in beta negative decay, we have a neutron that decides it wants to be a proton instead. So I'm going to end up with 1 more proton than I started with. But the numbers work out like this. So I have 6, I always take these numbers minus those to get these. So 16 minus a -1 will give me 17. Just like we did up here to find the thorium, you look up 17 on the periodic table because this is no longer a sulfur atom because it's not got 16 protons anymore. It's got 17 protons, which means that this is now a chlorine atom. See? Okay. And just like we did with the alpha decay, at the end of every single reaction, we're going to write plus gamma radiation. Okay? All right, good luck.